So is the construction of a von Neumann self-replicator more or less clear? Wonderful. Then let's make it confusing again. There's multiple steps of iteration one has to go through on the level to understanding. So what was the overall organization? We had the supervisory unit, the tape unit, the construction arm, or the construction unit, the tape unit, and the tape. And we can call all of this the machine R, and here is the tape. So this is the organization of the von Neumann's, or let's put the self-replicator. And the supervisory unit, we said, can be an arbitrary finite automaton interacting with the construction arm and with the tape. And there's two universalities hidden in its function. There is the Turing universality, and the construction universality. So when someone says a universal self-replicator, it is not at all clear what does it mean. It can be a self-replicator that happens to create an exact copy of itself and is able to compute, or it can be a self-replicator that can construct some infinite family of patterns that really encode some high variety of functionality. So it is important to have some insight that these two notions are actually independent. Like we can just build a Turing machine that is universal, which does not have a construction arm and that will not be able to make any copies of itself, and vice versa. We can have a universal constructor that is able to interpret an arbitrary description of a machine and build it, and is able to build a copy of it, but is not able to manipulate the tape in any way. So essentially, we could have just had the construction universality, but to be safe, it's nice to kind of assume both. And internally, this supervisory unit was encoding two machines, B and A. And B was the universal constructor. And A was the copy machine. That only if we have both can we both build the machine and copy the tape onto it. Copy machine. So let's maybe now take a step back and think of how is this related to the Kleene's recursion theorems. Maybe this is bothering some of you. So we can call this little section the hidden self-reference in the von Neumann self-replicator. So let us, for a moment, forget about the internal organization of R. So essentially, and let us just assume, okay, we just assume that R is computationally universal and construction universal. So suppose we have a cellular automaton and someone gives us a pattern without the tape and says, this is a universal computer and a universal constructor. Please design the content of the tape such that this pattern can self-replicate. So this is a good point to remember the Kleene's recursion theorems, because you could use them to exactly design the content of the tape, right? This is what we have talked about. So, not knowing anything specific about R, we can use Kleene's recursion theorems to design a content of the tape, some C, which is the binary sequence, which is an enriched quine, how we called them. Encoding the following instructions. So first, it instructs R to say construct a pattern with description R. So far, there is no self-reference. We are given R, and we just created a description of it on the tape. And here is where, so let's say this is as if we constructed a quine which first computes some computable function with some given index. And then we say obtain, or let's say then construct an empty tape as long as myself. So this is where we use the recursion theorems. We essentially say, obtain a description of yourself, compute its length, and construct an empty tape with exactly this length. And lastly, we say, copy myself on the tape. So this is the second part where we use the description of the quine that is now being copied. So if we were given a universal constructor and a universal computer, we could have used Kleene's recursion theorems to complete it into a self-replicator. But this is not what von Neumann did. In some sense, his construction is independent of the Kleene's recursion theorems, because he does not assume R to be just arbitrary, right? He is the designer of the pattern, so he has the freedom to assume that R can be split into two parts, into a part that is a constructor and into a copying machine. And here's the interesting thing. Once von Neumann self-replicator builds the new pattern, essentially what is on the tape is a quine with respect to R, because it will now be copied onto the new tape, but it is not an interesting quine, because by the point this copying is happening, the machine R has triggered the function of A, which is just a simple copying machine, which would copy anything that's on the tape, regardless of what is written there. It would be as to say that a document, like an actual physical paper with whatever is written on it, is a coin with respect to a printer, because if you insert it, it's going to make a copy. But it's not that the document instructs this printer to leverage its computational universality to build the copy. It's just a copying machine, right? So von Neumann's design feels intuitive because it feels like we have somehow escaped the self-reference. Like, once the content of the tape is being copied, we don't need it to be any kind of coin coming from a universal recipe. But every self-replicating process is deeply self-referential. You literally have to create a copy of yourself, so you have to somehow inspect yourself to build it. So where is the self-reference hidden in von Neumann's construction? Well, this is only apparent if we really view the interplay between the machine and the tape. That's because the tape actually contains the description of the machine, which means it contains both the specification of B, but also the specification of the copying machine, and it also specifies when should the copying machine start being active in order to copy whatever is on the tape. So the self-reference comes by the interplay of the tape and the machine. So we can summarize this by making the following distinction. First is the computational one, so programs, specifically quines, can come from universal recipes, let's say with respect to the universal Turing machines that, or Turing machine that executes it. This is what we have from Kleene's recursion theorems. It's like no matter what universal Turing machine you give me, some U, we can construct some coin Q such that when the universal Turing machine executes it on an empty input, we get as output the exactly Q. And then we can have somehow a physical variant of this. Physical self-replicators can come from universal recipes with respect to the underlying physics of the system. So this is a very informal discussion we're having. This is the whole lecture. The rest of the lecture today will be quite informal, so maybe I should have used the blue informal chalk. But what do I mean by this? So what is the physics in the case of a cellular automaton, or in the case of von Neumann's construction? That is the actual update rule of the cellular automaton and the elementary states. And here you can really see that von Neumann did not design the cellular automaton to exploit anything particular about it. He did not encode it such that, I don't know, the instruction signal which makes the construction arm prolonged 1 bit to the left has to have length 1. He really does not care. All he wanted to do is define an expressive enough system which can implement any kind of operation he can think of, like signal transmission, logic gates, creating pulses and like making new machines alive, movement and so on. And like from these higher level building blocks we were able to design a logical organization of a self-replicator. But once we had the laws of physics, we had complete freedom of how to define R. So we did not have to assume that R is an arbitrary universal constructor and a universal computer. We had somehow a freedom of how to design it. And this is exactly what von Neumann did. He designed it in such a way that self-replication did not have to deal with some complicated Quine constructions on the tape. But it's important to somehow believe that von Neumann's self-replicator should probably belong to this class, specifically because there is nothing particular about the CA rules that we exploited. And this is exactly why von Neumann's insight into the double usage of the tape's information and the logical organization of self-replication translates to other systems with self-replicators. If we did not exploit anything particular about the physics, then there's a good chance that von Neumann's construction case can say something about other physical worlds with other self-replicators, and this is exactly why his construction was able to say something about biological self-replication, because the world that we constructed was not convoluted in any way such that self-replication would only work in that world. Does this, at least on some intuitive level, make sense? So we can see this design as some sort of a physical analog of Kleene's recursion theorems, where if we are given rich enough physics, we could probably use some kind of recipe a la von Neumann self-replicator to build a self-replicating machine. But it is not clear how to precisely define what the rich enough expressivity is. So this is, let's say, in some sense, the open problem, and we will show that, for instance, counterintuitively, just having the underlying physics being Turing complete is not enough. This is, let's say, a new result by us. But now, maybe to really finish this chapter, let's spend the rest of this lecture by talking about von Neumann's future, or like visions for future work. As I said, he unfortunately died before he could really finish and complete his work. But from his manuscripts that were collected, completed, and published by Arthur Burks, you can see that really they were really rich with ideas that stemmed far beyond just the exact self-replicator construction in a cellular automaton. So for instance, cellular automata are nice because we could really abstract the logic of self-replication, but they are not necessarily very close to actual, or like they are not exactly physically feasible systems. Like for instance, we don't have conservation of mass or energy here, and yeah, we have a discrete world. So von Neumann did envision, let's say, a progression of models which would be more and more physically feasible, where he would conduct similar constructions. So one of them would be exactly to introduce more continuity, some rotational symmetries, conservation of basic quantities, and the other line that he cared for deeply was to introduce some probabilistic nature to the model, such that we can actually talk about self-replication in a noisy environment, which seems kind of crucial. that the self-replicator, like what would be the self-replicator design if its elementary particles have some small probability of actually producing the wrong output. Like how can we build reliable self-replicators? So this is exactly what we will just quickly list. So, yeah. So he did mention the, let's say, probabilistic model. So yeah, this is just a comment by von Neumann. So a true theory of self-replication should account for noisy environments. So one way to model this would be to consider a system where each elementary particle has some small probability epsilon of malfunctioning like a neuron misfiring. And he actually did consider such systems and did manage to publish a paper where he discusses some logical organization necessary to actually design computers or finite state automata that would work despite being built from these noisy parts. But to the best of my knowledge, I don't think there is a full construction of a self-replicating machine in a noisy environment. The second model he did mention was the excitation threshold fatigue model, which essentially was just a progression towards more physical feasibility, where now every cell of the cellular grid would be substituted by an artificial neuron based on the McCulloch and Pitts model, which was, I suppose, popular at the time of his work. So, yeah. So very simplistically, how could such an artificial neuron be defined? So it has connection to some neighboring neurons, and it can either be excited or unexcited. And essentially, the local update rule now, it's again a system with discrete states and discrete time. The neuron gets excited if the number of its neighbors that are excited exceeds a particular threshold, after which it enters a refractory period where it cannot get excited no matter what are its neighbors, after which it enters a relative refractory period where it can get excited if the number of its neighbors exceeds a threshold which is higher than when the neuron is fully rested. So in some sense, one way towards this would be to design a cellular automaton which is really rotationally symmetric, and it only depends on the number of its neighbors in each state and not necessarily the exact states. So, okay, let me just quickly write down this definition. So, a fixed threshold, let's say K, then enters refractory period where it does not get excited no matter what. And then enters relative refractory period where it only gets excited if number of excited neighbors is larger than sin k prime, which is larger than k. So let's say this is the first step towards more physical feasibility. Then he did mention the continuous model. Where now both time and space would be continuous, or at least time, no, time and space continuous. System governed by partial differential equations instead of the local update rule. That would not be unlike, let's say, some reaction diffusion. That would govern some processes in fluids or chemical substances. And lastly, he also did mention the basic, the conservation of some basic quantities that should be introduced into the system. Let's say mass, energy, and so on. And he did mention, for instance, for the kinematic model, adding some battery elementary particles that would serve as energy sources that could be somehow transformed. This is a critique of some people of cellular automata, that there we can just flip a quiescent state into a non-quiescent state. there's two points of view of how to deal with it. Either we can really view the quiescent state as the absence of matter and the non-quiescent state as the presence of some matter. And in this case, truly cellular automata, most of them are not mass conserving, but you can reduce yourself to a subset of cellular automata that are. There are some nice algebraic criteria to know whether it is mass conserving or not, for instance. But maybe the more natural approach is to view cellular automata as the informational layer, not really the matter. So we could introduce some layer of matter that would really be, let's say, some physical particles floating in space, and they would interact with each other in ways that are governed by the cellular automaton. So this would be some synthesis of von Neumann's kinematic model and the cellular automata model. But interestingly, to the best of my knowledge, I don't really know many works that would really progress on these, let's say, hierarchies of models beyond the cellular automata. Cellular automata seem to be very popular to still study self-replication, and this is actually what we will look into next time, is other examples of constructions. So I think this summarizes this. And we have the perfect time to discuss, let's say, or highlight, make a last highlight of some future work von Neumann envisioned. This is, in some sense, the most fundamental one. So far we have only talked about exact self-replication. And it makes sense because our motivating thought exercise was to colonize Mars. And if we were to build self-replicating machines that colonize a planet, it would be nice to ensure that each machine really builds an exact copy of itself, so that we ensure that its functionality will stay exactly the same, and we have complete control over what the machine does. If there could be some mutations and the offsprings could develop other functionality, this could be fatal both to the terraforming process but also to humankind. So let's say we can call these types of replicators maker replicators. We want them to make something for us, and there the exact self-replication is crucial. But there are other areas where it might be even more exciting to consider non-exact self-replication, such as the evolutionary processes. So indeed, von Neumann was interested in how can machines build offsprings that are not exact copies, but that are potentially more complicated than itself, which would really point at, at some process of open-ended evolution where the machines could really, over the lineage of the replicators, grow in complexity in some potentially unbounded manner, similarly to living systems. So yeah, we can have an informal definition of open-ended evolution. And grow in complexity in a potentially unbounded manner. And here I think it would be nice to actually cite a part of his text from the 5th lecture he gave at the University of Illinois. You can find this in the literature that I referenced in the notes. So he says actually much more than just what I now said. So anybody who looks at living organisms knows perfectly well that they can produce other organisms like themselves. This is their normal function. They wouldn't exist if they didn't do so, and it's plausible that this is the reason why they abound in the world. In other words, living organisms are very complicated aggregations of elementary parts. And by any reasonable theory of probability or thermodynamics, highly improbable. That they should occur in the world at all is a miracle of the first magnitude. The only thing which removes or mitigates this miracle is that they reproduce themselves. Therefore, if by any peculiar accident there should ever be one of them, from there on the rules of probability do not apply and there will be many of them. At least if the milieu is reasonable. But a reasonable milieu is already a thermodynamically much less improbable thing. So the operations of probability somehow leave a loophole at this point, and it is by the process of self-reproduction that they are pierced. Furthermore, it's equally evident that what goes on is actually 1 degree better than self-reproduction, for organisms appear to have got more elaborate in the course of time. Today's organisms are phylogenetically descended from others which were vastly simpler than they are, so much simpler in fact that it's inconceivable how any kind of description of the latter complex organism could have existed in the earlier one. It's not easy to imagine in what sense a gene, which is probably a low-order affair, can contain a description of the human being which will come from it. But in this case, you can say that since the gene has its effect only within another human organism, it probably need not contain a complete description of what is to happen, but only a few cues for a few alternatives. However, this is not so in phylogenetic evolution. That starts from simple entities surrounded by an unliving amorphous milieu and produces something more complicated. Evidently, these organisms have the ability to produce something more complicated than themselves. And crucially, von Neumann's self-replicator already hints at a logical organization that could achieve this evolutionary process. And this is very interesting. We introduced this universal constructor property to enable exact self-replication. But it turns out that this actually already suffices to have something more. And that is, the universal constructor is able to not only interpret a description of itself, but of arbitrary machine whose description it gets on the tape within the feasibility of the construction arm. So, for instance, it can also build machines that are more complicated than itself. So, if we imagine this self-replicator existing in some noisy environment where it undergoes some spontaneous mutations, then some of these changes could be lucky enough to result in tape descriptions of more complicated machines, and this would actually be phenotypically realized by the constructor. So we can summarize this in another informal definition. Evolutionary potential a self-replicator has an evolutionary potential if it can construct an offspring that is more complex than itself. That is more complex. So this is the crucial problem of the informality of this definition. This is for a so far unspecified formal notion of complexity. And the offspring in turn also has this property. So it has this property thereby resulting in a lineage of replicators of potentially growing unbounded complexity. And one way we can realize this potential is, for instance, by externally perturbating the tape with the description of the organism. So we can make an informal observation that the VNSR does have the evolutionary potential as it is a universal constructor. So yeah, the crucial problem is that we don't really have a formal definition of universal constructor, but that seems to be more troubling than the fact that, or like less troubling than the fact that we don't have a formal definition of complexity. And indeed, for instance, von Neumann did suggest to roughly approximate it by the number of elementary particles a replicator consists of, but avoided giving any really formal characterization of it. And maybe this would be a nice way to end with one final quote from von Neumann. After that, I promise this was the last one. Okay. So one cannot define the concept of complication correctly until one has seen in greater detail some critical examples. That is, some of the constructs which exhibit the critical and paradoxical properties of complexity. There is nothing new about this. It was exactly the same with conservation and non-conservation properties in physics, with the concepts of energy and entropy, and with other critical concepts. The simplest mechanical and thermodynamic systems had to be discussed for a long time before the correct concepts of energy and entropy could be abstracted from them. And I somehow argue this is, let's say, where the modern A-life is. It is in the process of creating a great number of examples. It is not always clear from the theoretical perspectives what do they show, but they undoubtedly show something interesting. And this will be, let's say, what we will finish this whole part about self-replication next time is we will do a quick overview of the constructions of self-replicators in cellular automata that came after von Neumann's self-replicator, and try to at least discuss what kind of properties do they have and what kind of properties do they have not. Yeah, so I think that's it for today.